Morning, everybody. Welcome back to Calc 2. Hope you all are enjoying this weather on this lovely 80-degree day. Oh, wait, that was a couple days ago. Hope you all are surviving this lovely cold snap before we return back to our hopeful April weather. Plan for today, as promised, I have a standard 12 quiz for you. Then we're going to jump into standard 13, start talking about alternating series. I've got my usual office hours for the next few days, and posted a web work yesterday that will be due on Friday over standard 13 stuff. Okay, so some of you have noticed that we're not going to probably get through as many standards as what the syllabus says by the end of the semester. Not terribly surprised. I kind of suspected at the beginning of the semester that might happen. So what I have for you today is a plan. So, goal is to get through 4 more standards before the end of the semester. It might end up only being 3. Gonna have to see how it goes. But assuming we get through 4 more standards, here is kind of a new updated grade charts of how many masteries do you need to get X grade in the class. There you go. So this is assuming we get through 16 standards. If we don't quite make it through all of these standards, then we'll get through at least 3 more. So if we only get 3 more standards, then subtract 2 from each of these numbers. But this is assuming we get through 16 standards. How many masteries you need in order to get whatever grade in the class. Something to keep in mind is that we are going to have one last midterm on the final day of the semester, plus a final exam. The last midterm and the final will have all of the standards on it from across the semester. So theoretically, you could have 0 masteries now and still get 2 masteries on everything from those 2 exams. I say theoretically because don't do that. But there are still opportunities for that, and as well as retests. I'll even let you do a retest during finals week outside of class. If you go on Canvas, Canvas is not currently up to date. I'll update Canvas once everybody's taken exam 2. Still a couple stragglers. Speaking of exam 2, nice job overall. Thought y'all did a pretty good job on this. Be happy to talk with you if you're concerned about your performance on this exam. I'll have solutions posted probably tomorrow once everybody's actually taken the exam. I'll put solutions up on Canvas. But in the meantime, if you want to talk with me about your exam D, I would be happy to do so. Yeah, that's about where things are at. Any questions or comments before we get started for today? So just so you all know, next we have 2 more standards related to, given a series, what are a test or tests that you can use to determine whether or not it converges. I'm particularly fond of today's test. And then that'll take us through probably partway through class on Friday, and then the last couple standards are looking at what if we tried to define a function in terms of x as being a series of some sort, which will lead us into a discussion of Taylor series by late next week. Can we get questions or comments before I pass out today's quiz? Alrighty. By the way, if you didn't get your exam back, then you were probably late to class and should feel ashamed of yourself. Come up, ask me after class, I'll give you your quiz. Or exam back. Alright. on. Don't pass that out yet. I've got a joke of the day. So, group of mathematicians and a group of engineers one day are traveling to a conference by train. The engineers all buy a ticket for themselves, but only one of the mathematicians buys a ticket. Of course, the engineers are ridiculing mathematicians, asking, wait, how are you going to get away with this? And suddenly one of the mathematicians yells out, hey, the conductor's coming! Quickly, all the mathematicians disappear into a single restroom. Conductor checks the ticket of each engineer, then knocks on the restroom door and says, ticket please. Mathematicians slide out their one ticket. Conductor checks it and leaves. A few minutes later, all the mathematicians come out. The engineers are all highly impressed by this trick. So when the conference ends, the same group of engineers, same group of mathematicians, takes the train back to where they came from. This time the engineers, thinking they're just as clever as the mathematicians, only buy one ticket for the group of them. The mathematicians don't buy any tickets at all. Engineers are asking mathematicians, wait, how are you going to get away with that with no tickets? And suddenly one of the mathematicians yells out, hey, the conductor's coming! All the engineers quickly disappear into a single restroom. Then one of the mathematicians knocks on the restroom door and says, ticket please. And the engineers are the ones who get in trouble. The idea being, mathematicians get the engineers one ticket, and then engineers are left with that when the actual conductor comes. Anyways, quiz time. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Quizzes in, please. Thank you. Alrighty, so here's the scoop. Last few classes we've started talking about a few different tests to determine whether or not a series is going to converge or diverge. For the most part though, we have something we haven't really looked at yet, or spent much time on, is what happens if you have some positive terms in your series and some negative terms in your series. Since mostly so far the tests we've been looking at, like the integral tests, require all the terms, bless you, that you're adding up to be positive numbers. What happens if you have something like -1 plus a half minus a third plus a fourth minus a fifth plus a sixth, where you have some positive terms and some negative terms? So, focus for today's standard is going to be how do we tackle a series like this and determine whether or not it converges? And some of the bananas bunker stuff you can get up to with a series like this one. So with that, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3. So to start with, I'm going to talk a little bit about a term that's even stricter than convergence, called absolute convergence of a series. Because that's going to be something that's going to be super helpful for us. So we're going to say that the series sum from n equals 1 to infinity of a sub n is going to be called absolutely convergent if, when we take the sum of the absolute values of every term in your series, that gives you a convergent series. So in other words, an absolutely convergent series is one where if you replace a sub n with the absolute value of a sub n, meaning you take every term in your series and you force it to become positive if that series happens to be convergent. So let's take a look at this series. Sum from n equals 1 to infinity of -1 to the n power over n squared. -1 to the n, having something like that show up in your series as a constant multiple, or as a multiple, not constant, usually it's like a quick and easy way to make it so that every other term becomes negative. Because if n is an even number, this is just +1. If n is an odd number, this will be -1. So if we were to take the absolute value of every term in this series the individual terms end up looking like? In other words, what would it look like if we took the absolute value of negative 1 to the n all over n squared, and we simplified that? Jonathan?
Will it be like the numbers on the top except all positive?
Yeah, all of our negatives become positive. So in other words, negative 1 to the n over n squared. This is going to simplify to 1 over n squared. Because the absolute value of negative 1 to the n, well, negative 1 to the n is always either going to be negative 1 or positive 1. And either way, if you take the absolute value of negative 1 or of positive 1, you're always going to get just plain old-fashioned 1. So if we take the absolute value of the top, it just comes out to 1. Absolute value of n squared, well, that's just n squared. And we end up with 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, etc., etc. With the idea being, we're taking every term in our original series and we're forcing it to become positive. Terms that are already positive, like a half and a fourth, we're leaving alone. Terms that are negative, like negative 1, negative a third, negative a fifth, etc., we are changing into their positive, we're changing to be positive instead of negative. So, question. Sum from n equals 1 to infinity of 1 over n squared. Maria, is that going to be a convergent series or a divergent series?
Convergent, yeah, because the p value is greater than 1.
Ah, because we have a p series and p is greater than 1? Yeah, exactly. That's something we saw in our last standard, is that when we have a p series, is that if you have a p series where your p, in this case 2, is some value greater than 1, then the series is automatically going to be convergent. So I'll put in here, it's p series, p is equal to 2, which is greater than 1. Sort of our explanation. So great. So when we take the sum from n equals 1 to infinity of just plain old vanilla 1 over n squared, we get a convergent series. And if this series is convergent, what does that tell us then about our original series, where every other term is negative? What does it have to be? James?
Convergent.
Oh, skipping ahead, are we? You're right. What I was going for is absolutely convergent. And then yes, the theorem at the bottom of the page will say because it's absolutely convergent, it also has to be convergent. My goodness, jumping the gun. But we could say that since the sum from n equals 1 to infinity of absolute value of negative 1 to the n over n squared converges, when we take away the absolute value, just take a sum from 1 to infinity of negative 1 to the n over n squared, that series must be absolutely convergent. Rhoda.
If it's n squared at the bottom, shouldn't the terms be negative 1 plus 1 half minus 1 fourth plus 1 9?
Holy moly, you're absolutely right.
Okay.
We're going to talk a lot later in class about what happens if you just have an n in the denominator, so I guess I jumped the gun on that. But yes, you're absolutely correct. That should be 1 4, or yeah, if n equals 2, this becomes plus 1 4th, minus 1 9th, plus 1 16, minus 1 over 25. Change that. But yes, good point. I know how to do n squared. I'm a mathematician. I'm not an engineer. The point still stands either way, though. This series, if you take the absolute value of each of the terms, all right, fine, I'll actually change this because harmonic series is not convergent, which is 1 plus a fourth, plus a ninth, plus a 16th, plus 1 over 25, etc., that is going to be a convergent series as a p-series with p equals 2, which is greater than 1. Therefore, the original series, where every other term is negative, is absolutely convergent. And so, James, what do we know then about absolutely convergent series?
If a series is absolutely convergent, then it's also normally convergent.
Yeah, exactly. And this is going to be our first theorem of today. And this is called the absolute convergence test. Where the absolute convergence test says if you have a sum from n equals 1 to infinity of a sub n that is absolutely convergent, then that same series also has to be plain old vanilla convergent as well. And the way you would prove that is using something in math called the triangle inequality, which basically says that if you're adding up a bunch of numbers like a1 plus a2 plus a3, and you're taking the absolute value of the whole sum, that's always going to be less than or equal to what you get if you take the absolute value of each of the individual terms and sum them together. Basically saying then if this sum ends up being convergent, then this thing which is less than that also has to be convergent using, say, the comparison test, is the idea here. So with that in mind, Nora. Actually, I'm going to ask you questions in a while. So Nora, with that in mind, if we go back to this original series, is this original series going to be convergent or divergent? Using this theorem.
Convergent?
Yeah, it's going to have to be convergent. We showed over here that it's absolutely convergent, and according to this theorem, any series that's absolutely convergent must also be plain old vanilla regular convergent as well. So we can kind of, if we go back over here, that's going to tell us that the sum from 1 to infinity of negative 1 to the n over n squared is convergent by the absolute convergence test. So the idea behind this test is if you take all of your terms in your series and you change them to all be positive, if the version of your series where every term is positive happens to converge, then your original series is also going to have to converge, where you may have some positive and some negative terms that are mixed in. Any questions or comments about this before we look at a couple more examples? Yeah, Bethany?
Is this like absolute value, is that the thing on the left hand or the right hand in that example?
So in this case, this would correspond to if we were to take like the absolute value of the entire series, and this corresponds to if we're taking the absolute value of each term individually and adding them together. And the idea being if this thing happens to converge, then that means the absolute value of the original series, where we've added everything up and then taken the absolute value all at once, would have to converge. And then if this thing converges, that means the original series or its negative would both have to converge. Let's look at a couple more examples. So I'm going to flip on to page 2 now. How about some from n equals 1 to infinity of a sub n, where if we start adding up each term individually, we're going to get 1 plus 1 over 2 cubed minus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed minus 1 over 6 cubed plus 1 over 7 cubed plus 1 over 8 cubed minus 1 over 9 cubed, etc., etc. Where every third term in our series is going to be negative. Well, 1 over 3 cubed, the 1 over 6 cubed, the 1 over 9 cubed terms are all negative, but every other term in the series, first, second, fourth, fifth, seventh, eighth, etc., are all positive. And I want to determine whether or not this series converges. So let's ask this question. We're going to take a sum from n equals 1 to infinity of the absolute value of each term. Nolan, how would taking the absolute value of each term individually change what's in our series? So in other words, just looking at these terms, kind of what would change if we're taking absolute values of each term?
Well, it turned into a P series, right?
Yeah, specifically what P series?
Well, that convert does P is greater than
What's our P here?
3.
Yeah, we could write this as a sum, in other words, from n equals 1 to infinity of 1 over n cubed. And as Nolan pointed out, hey, we know something about that series. We know that's a P series, where a P, in this case, is 3. As a P series, where our P value is 3, which is greater than 1. And Gabe, if the series we get when we take the absolute value of each term turns out to be convergent, what does that tell us about the original series?
So, if its absolute value is convergent, that means it's absolutely convergent.
So that's going to tell us that the original sum is absolutely convergent by definition, because when we took the absolute value of each term separately and added them together, meaning when we took each term and forced them to all be positive, we got a convergent series. So that was our definition for what it means for the original series to be absolutely convergent. And if the original series is absolutely convergent, Rhoda?
That means that the actual series is convergent.
Bingo. By the absolute convergence test, that means that our sum from n equals 1 of a sub n, as n goes from 1 to infinity, is convergent by the absolute convergence test. Questions or comments about this one? Yes?
When writing this out, can we kind of skip that in between step of saying that it's absolutely convergent, therefore it's convergent? Or,
Okay. Do you have another way to show that the series up here is convergent?
No, I mean when you write it.
Oh, you mean just go say this converges, therefore
Yeah.
the original series is convergent by the absolute convergence? Sure.
Okay.
Yeah, that's fine. I was gonna say, you should give a little bit of explanation for why it's absolutely convergent, or why, when you take this series, why is that convergent, which is it's P series, P is greater than 1, as Nolan pointed out. But yeah, you could skip this line right here if you wanted to. I'm writing it up just to make everything as clear as I can, but honestly, if I was doing this on a quiz or exam myself, I probably would skip that line. Alright, Rotom, now let's look at the series that I actually wanted to look at on the front page, which is this thing, but we've replaced n squared with n. So we'll have sum from n equals 1 to infinity, negative 1 to the n plus 1 power, all over n. Which, in this case, if we start plugging in values for n, we'll get 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, etc., etc. So, James, what do we get if we take the absolute value of each term of this series?
Won't it just be 1 plus a half plus a third plus a fourth?
Yeah, we're just taking every term which makes it positive.
Yeah, which is then just 1 over n.
Yeah, so this just becomes the sum from n equals 1 to infinity of 1 over n. Aiden, does that series converge?
I think it diverges due to P series because P is equal to 1.
Yeah, so this is the harmonic series, you may remember from Standard 12, which was sort of the P series where P equals 1, and in the case where P is equal to 1, the series is going to diverge. It only converges if P is strictly greater than 1. So with that in mind, that's going to tell us then that our original series, sum from n equals 1 to infinity of negative 1 to the n plus 1 all over n, turns out that is not going to be an absolutely convergent series. Because if it was absolutely convergent, then when we took the absolute value of each term, we would expect to get something that converges by definition. So Jonah, it would seem that we have a series that's not absolutely convergent. Can we use that to say anything about whether the original series is convergent or divergent?
I was gonna ask the same thing actually, but I'm gonna guess no.
No? We can't say anything?
Yeah. I don't know.
Yes, we can't say anything, or yes, you're changing your mind?
Yes, we can't say anything.
So if we look at what the absolute convergence test says, it says if your series is absolutely convergent, then it has to be convergent.
But if it's not, then you don't know anything. Does it tell you anything about it?
Yeah, it doesn't say the other way around. It doesn't say that a convergent series has to be absolutely convergent. I would say the absolute convergence test doesn't tell us anything here. So, turns out, just because the series isn't absolutely convergent, it still could be plain old vanilla convergent. absolute convergence test only tells you something that if it's absolutely convergent, then it has to be convergent, but if it's not absolutely convergent, it could be convergent or divergent. So it turns out we're going to need another test to tell us whether this series is convergent or divergent, this alternating series. By the way, this series has a special name. It's called the alternating harmonic series. I'm going to have a lot to say about this series later. So, the absolute convergence test doesn't tell us anything about this series. And how can we tell if it converges or not? Well, turns out we have another, it turns out, do y'all remember the divergence test from a couple standards ago? Where the divergence test said something like, if A sub n does not converge to 0, then the sum of all the A sub n diverges. If the individual terms that we're adding up did converge to 0, Allie, if the individual terms we're adding up converge to 0, what did that tell us about the original series?
From the divergence test, it didn't tell us.
Yeah, it told us the original series, well, it could converge, but it could also diverge. And the divergence test, so just like the absolute comparison test, this theorem only worked one way, that if the individual terms did not converge to 0, then it has to diverge, but if they did, the test doesn't tell us anything. Turns out, in the case of having an alternating series, where your terms alternate between plus minus, plus minus, plus minus, plus minus, dot, 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 it turns out that if you have an alternating series, then this condition actually will guarantee your series converges. And that is called the alternating series test. On page 3 now. Where the alternating series test says, if B sub n is a positive decreasing series converging to 0, or sequence, excuse me, meaning each term is greater than the one that comes after it, and the limit as n goes to infinity of B sub n is equal to 0, then the alternating series sum from n equals 1 to infinity of -1 to the n plus 1 times B sub n, which is the series you would get if you took B1 minus B2 plus B3 minus B4 plus B5 minus B6 must converge. So in other words, if you have an alternating series where the terms in your series go plus minus, plus minus, plus minus, plus minus, or you could go minus, plus minus, plus minus, plus. Where you start doesn't matter as long as it's alternating after that first term. Then, if the individual terms in your series go to 0, that will be enough to tell you that the original series has to converge. So let's take another quick look at this alternating harmonic series. Sum from n equals 1 to infinity of -1 to the n plus 1 all over n. If we take the absolute value of each term and write it as b sub 1 equals 1, b sub 2 equals positive a half, b sub 3 is positive a third, b sub 4 is positive 1/4, etc., etc. And say if b sub n is going to be the absolute value of -1 to the n plus 1 all over n, which in this case is 1 over n. Katie, is each term b1, b2, b3, b4 bigger than the one that comes after it? It's not? Which term is smaller than one that comes after it?
All, like, smaller, like, all,
Oh, is one bigger or smaller than a half?
small, oh, sorry, bigger, I bring it backwards. It's bigger than 1/2. And
1/2 versus a third?
Bigger, yeah.
Yeah, in fact, each one is bigger than the one that comes before it. All right, follow-up question then, Katie. I'll test you on this one. If we were to take a limit as n goes to infinity of these b sub n's, meaning if we take a limit as n goes to infinity of 1 over n, what would we expect to get? Meaning as n gets bigger and bigger and bigger and bigger, what's going to happen to 1 over n? What's it going to get closer and closer to?
0.
Yeah, exactly. So in this case, if we take the individual terms, where if we force them to all become positive, then we're going to get this sort of decreasing sequence of terms, b1 greater than b2, greater than b3, greater than b4, etc., etc. And when we take a limit as n goes to infinity of these individual terms, they're all going to 0. Anna, what's that going to tell us then about the alternating harmonic series?
It converges.
It has to converge by the alternating series test. The sum from n equals 1 to infinity of -1 to the n plus 1 over n converges. So even though the alternating harmonic series, it's not absolutely convergent. If we take the absolute value of each term and add them all up, we don't get a convergent series. If we change half of every other term to being negative, this series is in fact going to converge to something. By the way, out of curiosity, does anybody know what this series converges to? It's not something that's obvious. What's that?
Pi is like pi.
Good guess, but no. This one doesn't involve pi. It actually converges to natural log of 2. If you take 1 minus a half plus 1/3 minus a fourth plus 1/5 minus a sixth, etc., etc., you can actually, it's pretty difficult to show this, so we're not going to do that in class, but you can actually show this series converges to the natural log of 2. Go figure. I wouldn't have guessed natural log has anything to do with this. I wouldn't have guessed that natural log has anything to do with 1 over n or 1 over x. There couldn't possibly be any relationship there. Any questions or comments? So basically, what the idea here behind the alternating series test is it allows you to say that the divergence test does work backwards in the case of an alternating series. That if you have an alternating series where you go plus minus, etc., where the individual terms go to 0, then your alternating series would have to converge. Something that's true for alternating series, not necessarily true for plain old vanilla series. By the way, we have a special name for a series like this where it's convergent but not absolutely convergent. We call it conditionally convergent. So, here, I'll put this over here, but we're going to say that a sum from j equals 1 to infinity of c sub j is conditionally convergent if your series is convergent but not absolutely convergent. So in the case of convergence, but a non-absolutely convergent series, we call it conditionally convergent. And our example of this would be the alternating harmonic series, where if we take the absolute value of each term and add them all up, it's a divergent series, but without taking absolute value of each term as is, it's convergent. All right, y'all are looking a little restless. Do y'all want to see something really fun in the last few minutes of class? All right, here's something fun. You may disagree with this being fun. I think it's fun. Let's look at the next page for just a second. I'm going to take this alternating harmonic series. Let's get ahead of you. Sorry, just a second. If we were to take 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh, we know that natural log of 2 is going to be the limit of this alternating harmonic series now. What I'm going to do is I'm going to take this series and I'm going to rearrange some of the terms. I'm just going to write it as 1 minus a half minus a fourth plus a third minus a sixth minus 1 over 8 plus 1 over 5 minus 1 over 10 minus 1 over 12, etc., etc. So all I'm doing is I'm taking the terms in the original series and I'm moving them around a little bit. And I'm pulling the fourth out in front of the third, a fifth gets moved back to behind a sixth and an eighth, but it's all the same terms. Except now, I'm going to put some stuff in parentheses here. After I put this in parentheses, we're going to get 1/2 minus a fourth. A third minus a sixth, that's positive 1/6, minus 1 over 8. 1/5 minus a tenth, that's positive 1 over 10, minus 1 over 12, etc., etc. James, if I were to factor a half out of this expression, what would we be left with?
1 minus a half plus a third minus a fourth.
That's looking familiar. Oh hey, that's just the 1/2 times the alternating harmonic series again, which is going to converge to 1/2 natural log of 2. So what did we just show? We just showed that natural log of 2 is equal to 1/2 natural log of 2. If we start at the top and look at where did we end up, which is the same if we divided both sides by natural log of 2 as saying 1 is equal to 1/2. Everybody on board with that? Have a good day, everybody. We'll continue this conversation on Wednesday. So Wednesday's class will finish Standard 13, and then start towards the end of class we'll start Standard 14. With the idea of finishing Standard 14 in Friday's class. So that, hope y'all have a good one, and I'll see you all on Wednesday. You didn't pick up your exam, if you didn't get your exam earlier because you showed up late, I'd be happy to give that to you now.